We've spent some time talking about functions of multiple variables and discussing the differentiation of these functions, but we want to move now and start talking about the integration of these functions. And what we find is that a lot of the techniques and ways of approaching multivariable functions from a differentiation standpoint are similar to the way we would approach them from an integration standpoint. So consider the idea of this function, 6xy squared. If we want to integrate with respect to x, then if you recall from the way we do partial differentiation, we would hold the y value constant and take derivatives only with respect to the x variable. So we do the same thing when we take integrals with respect to a specific variable. Now we don't call them partial integration, or at least I've never heard that. But if we integrate this function with respect to x, for practical purposes, the 6 and the y squared are they're constants. So what we do is we add 1 to the power of x, and then we divide by that power. So instead of the 6, that divides by 2 into 3. So we have 3x squared y squared. Now we still have a constant because this is an indefinite integral, but you might wonder why that's a constant with respect to y. And the reason that is because not only does that constant include just numbers, but it might include some variables in y. And the reason for that is because if you remember, one of the ways that you can check to see if you've integrated correctly is to take the derivative of this, and you should get this quantity back. Well, if I take the partial derivative with respect to x here, the partial derivative with respect to x of this comes back here. The partial derivative of any numbers or any expression that only has y alone in it will go to 0. So we need to make sure that our little change, or that dangling piece of constant, contains y. Similarly, if we integrate with respect to y, we hold the x and the 6 constant. So we add 1 to the power of y, and then we divide by 3, so 6 divided by 3 is 2. And we have some constant which is a function of x. And this happens again because if we take the partial derivative with respect to y, we get this piece, and all of this would have to be 0 because any expression in x alone or any number would derive to 0. So that's that makes sense probably. The indefinite integral is probably not a big issue, but definite integrals are a little trickier maybe to wrap your head around. So let's take a look at the same expression integrated with respect to y here. So I have limits of integration 1 and 3. So we know that the antiderivative here is 2xy cubed, and that goes from 1 to 3. So I plug in 3 for my y, for wherever I see my y, and I plug in 1 for wherever I see my y. And that comes out to be 54 minus 2, or 52x. So what I notice here is when I integrate, I still have an expression in x. But what's even more interesting is I don't have to integrate with just numbers as my limits. I could actually use functions of x as my limits, because from y's perspective, any expression in terms of x is actually a constant value. So these are just constant values as far as the limit of integration is concerned. So when we integrate through, we do the same thing, but instead of numbers here, we have expressions in terms of x. So multiplying that out, you get 2x to the 7th minus 16x to the 4th. So what we're going to find is by defining limits in terms of functions, we can do really interesting things as we start to integrate functions with multivariable functions. So just stick around and we're going to do some examples putting all this together.